In this video, we'll be proving proposition 1.4.2. If you want to look back at what that was, for any vectors v and w in R3, we have that the length is equal to the length of w, length of v sine theta, where theta is the angle between them. And we also have that this length of the cross product is the area of the parallelogram formed by v and w. So we will prove these 2 points using an identity that's called the Lagrange identity, which says that the length of v cross w squared is equal to the length of v squared, length of w squared minus v dot w squared. So you notice it involves both the cross product and the dot product here. This Lagrange identity can be proven by just expressing the two sides of the equality using the components of v and the components of w. So we'll skip it just because it doesn't enlighten in any ways, but we'll start with it and we'll prove the other two. And I think those parts are more interesting. All right, so first part, we want to look at the length of v cross w squared. And we want to get at the length of v, length of w sine theta. All right, so let's start with this Lagrange identity. So this is identity 1.1 that I'm using. All right, now I'm going to use what we know about the dot product. The dot product, we actually proved using the cosine law that this was length of v, length of w, cos theta, and then we square it all. So at this point, I can factor out length of v squared, length of w squared. From the first term, I have nothing left, so I end up with the 1. From the second, the only part that I haven't pulled out is the cosine, and so I'll get 1 minus cosine squared, and so that would give v squared, w squared, and 1 minus cosine squared, that's sine squared theta. All right, now we want the length itself, not the square, so I have to take a square of the other side. Now it's tempting to think, well, the square root and the squares will cancel, but there's a little issue. When the square is inside, they don't quite cancel. You get the absolute value. So absolute value of v, length of w, sine theta. And now, well, the lengths are clearly positive, so this is positive because they're lengths. And this part here, the sine theta, is positive because if you remember from the proposition, I did say you have to take the angle between 0 and 180. And so because theta is between 0 degree and 180, that means we're on the top half of the circle. We're over here, and so sine theta is positive. And so we actually, in this case, can get rid of the absolute value, and we get length of v, length of w, sine theta. All right, now we want to use this to relate the length of the cross product with the area of the parallelogram. So let's draw the parallelogram. I have v here. I have w over here. And let me add h, just the height of the parallelogram. And if you remember, this angle was theta. So before we get started, I want you to tell me what sine theta would be. Sine theta is opposite over hypotenuse. So let's look at this small triangle here. So sine theta is opposite, which is h, over hypotenuse, which is length of v. All right, so let's get back to this length of v cross w. We just proved in part 1 that that was length of v, length of w, sine theta. Now I'm going to replace sine theta by h over v. So I get length of v, length of w, h over v. The length of the v's cancel, and I get length of w times h. Well, h was the height. The length of w is the base, so this is base times height. And so it is the area of the parallelogram. All right, not so bad, not so bad. Let's look at this corollary. A corollary is just a consequence of a proposition or a theorem. So it's something that follows pretty directly that you don't have to work tons for. If V and W are in R3, again, for this entire section, we're looking at R3 because that's the only place where we could define the cross product. V cross W equals 0. That tells you that V, now careful, for the dot product, V dot W is 0 if they're perpendicular. Here it's not the same thing. It would give you 0 if they're parallel. Right, let's see why that's true. If V cross W equals 0, notice 0, vector, right? The cross product is a vector. That means the area of the parallelogram, which is the length of V cross W, is 0. So if the cross product is 0, the parallelogram has 0 area. That means the parallelogram is flat. That's the same thing. And so V is parallel to W, right? If the two vectors you're using to build your parallelogram are parallel, then you're just going to get something VW, VW. You're going to get something completely flat. So this means that we can use the cross product to test if things are parallel. Now, it's not necessarily faster than doing the ratio, which is what we did before, so it's up to you. If you like the cross product, you can use the cross product. If you like the ratios, you can use the ratios.